Algorithmic trading with machine learning. Machine learning is revolutionizing algorithmic trading by providing powerful tools for analyzing large datasets, identifying patterns, and making predictions with greater precision. In this script, we'll explore how machine learning is applied in trading, focusing on two major learning paradigms: supervised learning and unsupervised learning. Understanding these paradigms is essential for traders looking to harness machine learning to enhance their strategies, optimize performance, and manage risk effectively. Number 1. Supervised versus unsupervised learning. In algorithmic trading, machine learning is typically divided into two main approaches: supervised learning and unsupervised learning. Each serves a different purpose and addresses various types of problems. Supervised learning is when a machine learning model is trained on labeled data, meaning the outcome or target variable is known. The model learns to map input features, like historical price data, to specific outcomes, such as whether a stock will rise or fall. As the model trains, it continually improves by minimizing the difference between predicted and actual outcomes. Some of the most commonly used algorithms in supervised learning include linear regression. This algorithm models the relationship between one or more independent variables and a continuous outcome. Traders often use it to forecast asset prices. Logistic regression. Logistic regression helps traders predict binary outcomes, such as whether the market will be bullish or bearish, which is essential for decision-making. Decision trees. By breaking data into subsets based on key features, decision trees help visualize possible decision paths and outcomes in trading. Support vector machines, SVMs. SVMs are great for classifying complex data. They identify optimal boundaries between different market conditions or price movements. Neural networks. With their ability to detect complex, nonlinear patterns, neural networks are particularly useful for forecasting trends or detecting intricate price movements in the market. Applications in trading. Supervised learning is highly versatile in trading. For predictive modeling, it's used to forecast future prices based on historical data and market signals. In classification, it helps categorize market conditions, such as whether a stock will outperform or underperform a benchmark. Lastly, it can be used for signal generation, where models identify patterns that could lead to buy or sell signals. Unsupervised learning. Unsupervised learning, on the other hand, works with unlabeled data, meaning there are no predefined outcomes. The goal here is to find hidden patterns or structures within the data. This is particularly useful for traders looking to uncover new insights in the market without prior assumptions. Common algorithms. Popular unsupervised algorithms include clustering. Techniques like K-means group similar data points together, which traders use to segment markets or identify stocks with similar behavior. Principal component analysis, PCA. PCA reduces complex datasets to focus on the most significant variables, helping traders visualize trends and price changes more clearly. Anomaly detection. Methods like isolation forest identify outliers in the data. This helps traders detect unusual market behavior, which can serve as an early warning for potential opportunities or risks. Applications in trading. In unsupervised learning, market segmentation through clustering allows traders to group assets that behave similarly, making it easier to develop targeted strategies. Feature extraction, using methods like PCA, can simplify large datasets by focusing on the most important variables. Finally, pattern recognition enables traders to detect hidden market trends that they can incorporate into their strategies. Comparative insights. When comparing supervised and unsupervised learning, it's essential to consider data requirements. Supervised learning requires labeled data, which can be expensive to obtain, while unsupervised learning offers more flexibility with unlabeled data. Model complexity. Supervised models tend to be more straightforward and easier to validate since they focus on achieving specific outcomes. In contrast, unsupervised models can be more abstract and harder to interpret. Use cases. Supervised learning excels at tasks like price prediction, signal generation, and classifying market conditions. Unsupervised learning, however, is more exploratory and valuable for tasks like market segmentation or discovering hidden patterns in data. Number 2. Feature engineering and selection. In machine learning, feature engineering is crucial for transforming raw data into useful features that improve a model's performance. Feature engineering. Some common techniques include creating new features. Traders often derive new variables from historical price data, like moving averages or volatility measures, to help detect trends or market sentiment. Feature transformation. By normalizing or scaling data, traders make sure that variables with different scales don't unfairly influence the model's performance. Feature interaction. Combining variables such as trading volume and price changes can reveal new relationships that weren't apparent before. Feature selection. Feature selection is the process of choosing the most relevant features to include in a model. This helps enhance accuracy and reduces the risk of overfitting. Filter methods use statistical techniques to determine which features are most important. Wrapper methods involve testing different subsets of features to see which combination works best. Embedded methods, such as decision trees, select important features during the training process, automatically penalizing irrelevant ones. Number 3. Model evaluation and improvement. In algorithmic trading, building a machine learning model is just the first step. To ensure it performs well in real-world scenarios, rigorous evaluation and continuous refinement are necessary. This section outlines key methods for evaluating models and strategies to enhance performance over time. Model evaluation. Let's talk about evaluation metrics. When it comes to trading, the way you assess your model's performance will depend on the type of task, classification, regression, or even time series forecasting. There are a few key metrics that can help you gauge how well your model is doing. Accuracy is probably the most familiar. It measures the percentage of correct predictions your model makes. But be careful. In trading, accuracy alone isn't always enough, especially when you're dealing with imbalanced data or uneven class distributions. Next, we have precision and recall. Precision shows how many of your predicted positives were actually correct, while recall indicates how many of the actual positives your model managed to capture. In trading, these metrics are crucial because false positives and false negatives can have very different consequences. For example, predicting a rise that doesn't happen can lead to losses, and missing out on a profitable trade can cost you valuable opportunities. The F1 score is another handy metric. It balances precision and recall, which is useful when you're dealing with imbalanced data, as is often the case in trading. For regression problems, you'll want to pay attention to mean absolute error, MAE, and mean squared error, MSE. These measure how close your predictions are to the actual values. MSE penalizes larger errors more, so it helps you focus on minimizing the biggest mistakes, which is key in trading. For overall strategy performance, nothing beats the Sharpe ratio. It measures the risk-adjusted return of your strategy, helping you assess how well your trading model compensates for the risk it's taking on. Number 4. Cross-validation. Next up is cross-validation. This technique helps you understand how well your model generalizes to new data, which is crucial to avoid overfitting. In algorithmic trading, we typically use 2 types of cross-validation. K-fold cross-validation splits your dataset into multiple parts. The model is trained on several parts and validated on the rest. This process is repeated multiple times, giving you a solid understanding of how your model performs overall. For time series data, we use time series cross-validation, which respects the order of the data. This means training on earlier data and testing on later data, which reflects the real-world conditions of trading. Number 5. Model calibration. Now let's talk about model calibration. This step is all about adjusting your model's parameters to improve performance. Hyperparameter tuning is a common method. This involves optimizing key parameters like learning rate or regularization through techniques like grid search or more advanced methods like Bayesian optimization. You can also boost performance with ensemble methods, which combine several models to create a more robust, accurate result. Techniques like bagging and boosting help minimize individual model weaknesses. Model improvement. Improvement is an ongoing process in algorithmic trading. One key area to focus on is feature engineering and selection. Adding new features based on emerging market trends can significantly enhance your model's predictive power. Use feature importance analysis to determine which features are truly contributing to your model's success, and remove the ones that aren't. This makes your model leaner and better at generalizing to new data. Next, let's touch on model updates and retraining. The market is constantly changing, so your model needs to evolve with it. You'll want to periodically retrain your model using the most recent data to ensure it stays aligned with current market trends. Another option is adaptive models, which can update themselves incrementally as new data comes in. This reduces the need for complete retraining sessions and keeps your model responsive to change. Number 6. Performance monitoring. Lastly, let's talk about performance monitoring. Once your model is live, it's crucial to keep an eye on it in real time. Real-time performance tracking of key metrics like trading performance, risk measures, and execution efficiency is vital. This allows you to identify any issues early and make necessary adjustments. You can also implement anomaly detection systems to alert you if the model starts behaving abnormally. This can help you catch performance drops or unexpected behaviors quickly. By focusing on rigorous evaluation, regular updates, and real-time monitoring, you can ensure your algorithmic trading model stays competitive and adapts to the ever-changing markets. Conclusion: machine learning has revolutionized algorithmic trading by enhancing predictive power, uncovering hidden patterns, and enabling more efficient trading strategies. By understanding supervised and unsupervised learning, applying rigorous feature engineering and selection, and continuously refining models, traders can stay ahead in today's fast-paced financial markets. With these tools, traders not only gain deeper insights into market behavior, but also manage risk more effectively, ensuring smarter, data-driven decisions in their trading strategies.